A battery just passed a test that the engineers running it did not fully believe was possible until the numbers appeared on their screens. Not a controlled laboratory test, with ideal conditions, carefully managed to produce the best possible result. A real-world test, a real vehicle, a real road. And when the energy density figure came back from the independent verification facility, not from CATL's own labs, not from a press release, but from a certified third-party testing center with no commercial interest in the outcome, engineers at BMW, Tesla, and Panasonic all requested the full dataset before they would accept what the headline number implied. The number was 500 watt-hours per kilogram. If that does not immediately mean something to you, it will in about 90 seconds. Because that number does not just represent a better battery. It represents the moment of physical ceiling that every engineer in the industry had been working around for 30 years, got quietly removed. And the company that removed it already supplies the batteries inside more than a third of every electric vehicle currently driving on any road on Earth. They were not supposed to be able to do this yet. The timeline the rest of the industry had built its strategy around said this was a 2030 problem at the earliest. A 2035 outcome if things went slowly. CATL just delivered it in 2023. And the way they delivered it, the specific approach they used, was not the approach anyone else was running. Which means every competitor's roadmap just became significantly less relevant than it was the day before the announcement. If understanding what just shifted in the global technology race is the kind of thing you want to know before the rest of the world catches up, hit subscribe right now. Because this story is about to get considerably larger than one battery announcement. To understand why 500 watt-hours per kilogram matters so much, you need to understand the wall that every battery ever built has eventually hit. Not a regulatory wall, not a manufacturing wall, a physics wall. The kind that does not move because engineers work harder or spend more money. Every battery stores energy through a chemical reaction between two electrodes, a positive and a negative, with a substance called an electrolyte carrying charged ions between them. The more tightly you can pack energy into that system, the higher the energy density. Higher density means more range in an electric vehicle, longer life in a phone, more power in a smaller and lighter package. For 30 years, engineers across every major battery company in the world have been pushing that density number higher, and for 30 years they have been hitting the same ceiling. Past a certain point, the chemistry becomes unstable. More energy packed into a smaller space means more heat generated during charging and discharging. More heat means higher risk of what engineers call thermal runaway, the chain reaction where one overheating cell triggers the next, which triggers the next, which produces temperatures high enough to ignite the liquid electrolyte and turn a battery pack into an uncontrollable fire. The Samsung Galaxy Note 7 made this phenomenon globally famous in 2016. Phones catching fire on desks, in pockets, on airplanes. But the Note 7 was not a uniquely bad product. It was a product that pushed energy density aggressively and encountered the ceiling that every lithium battery eventually hits. The industry's response was not to solve the underlying problem. It was to engineer around it. Sophisticated cooling systems added to manage heat. Buffer zones built into pack designs to slow thermal propagation. Safety margins programmed into charging software to keep cells away from conditions where instability becomes dangerous. All of which added weight. All of which added cost. All of which partially canceled out the energy gains that drove the density push in the first place. This is the fundamental economics that has defined battery development for 3 decades. You push density up. The physics pushes back. You add safety systems to manage the physics. The safety systems add weight and cost that reduce the practical benefit of the density gain. You push density up again. The physics pushes back harder. Most engineers in the industry had internalized this cycle as a permanent feature of electrochemistry. Not a problem to be solved, a constraint to be optimized within. The question was not how to remove the ceiling. The question was, How to get as close to it as safely possible. Cattle asked a different question entirely, and the answer they found was sitting in a branch of physics that most people learned about once in school and then never thought about again. The question Cattle asked was not how to push harder against the ceiling. It was why the ceiling existed at all. And the answer, when they traced it back to its origin, pointed at something almost embarrassingly fundamental. The ceiling existed because of liquid. The electrolyte, the substance carrying ions between the electrodes, was a liquid. And liquid was the source of every problem. Liquid is what makes thermal runaway possible. When a cell overheats, a liquid electrolyte can combust. Liquid is what limits how tightly you can pack the energy, because liquid under pressure and heat behaves in ways that are difficult to contain safely. Liquid is what requires all the cooling systems and safety margins that add weight and cost. Remove the liquid, and you remove the source of the ceiling. This reasoning is not new. Solid-state batteries, replacing the liquid electrolyte with a solid material, have been the stated goal of almost every major battery research program in the world for the past decade. Toyota has been promising solid-state EVs since 2017. QuantumScape, backed by Volkswagen with billions in investment, has been in development since 2010. Samsung SDI, Panasonic, and a dozen well-funded startups have all been working on variations of the same approach. None of them are in mass production. None of them have reached 500 watt-hours per kilogram in verified real-world conditions. And none of them were working on the specific approach Cattle used, because Cattle did not build a solid-state battery. They built something that exists between solid and liquid. And understanding what that actually means requires revisiting something most people learned in school and promptly forgot. Matter exists in 4 states that most people can name without thinking: solid, liquid, gas, plasma. These categories feel complete, the full inventory of what matter can be. But here is what most people will never hear about the physics they were taught. Those 4 categories describe the gross behavior of matter at scales humans can observe directly. At the molecular and quantum level, matter can exist in configurations that do not fit cleanly into any of those 4 boxes. Configurations where molecules are packed so tightly that they begin sharing quantum mechanical properties, where the distinction between solid and liquid becomes genuinely ambiguous, where the material conducts ions, the charged particles that carry energy through a battery, with the efficiency of a liquid, while maintaining the structural stability of a solid. Physicists call this condensed matter. Cattle calls their version of it a condensed matter electrolyte. And before you assume this is marketing language designed to make something ordinary sound impressive, the independent testing data says otherwise. Here is what Cattle actually built. The condensed matter electrolyte is not a solid, and it is not a liquid. Its internal molecular structure is packed at densities that force the constituent molecules into collective quantum behavior. They move and conduct not as independent particles, navigating through a medium, but as a coordinated system, sharing energy states. The result is a material that achieves ion conductivity comparable to liquid electrolytes. Ions move freely and quickly, which is what allows fast charging and efficient discharge, while having none of the thermal instability that makes liquid electrolytes dangerous under stress. There is no liquid to combust. There is no fluid to expand under pressure. The thermal runaway pathway that has defined battery safety engineering for 30 years does not exist in this chemistry. Not because it has been managed or engineered around, but because the physical precondition for it is absent. The safety testing results that accompanied the verified energy density figure were as significant as the density number itself. Nail penetration test: a fully charged cell punctured with a steel nail at operating speed. No thermal runaway. No fire. Temperature rise within controlled parameters. Crush test: mechanical compression beyond any real-world scenario. Same result. Thermal stability testing at extreme temperatures, both high and low, beyond the range of any commercial operating environment. Consistent performance throughout. In every test condition that has historically triggered catastrophic failure in lithium battery chemistry, The condensed matter design produced outcomes that conventional engineering would describe as impossible. And then there is the number that stopped the room. 500 watt-hours per kilogram. Verified. Independent. Real. To make that number land with the weight it deserves, conventional lithium batteries considered excellent by current industry standards achieve approximately 300 watt-hours per kilogram. The best-performing cells from any manufacturer before this announcement reached roughly 330 to 350 under optimized conditions. 500 is not a marginal step forward. It is not the next point on a curve that has been advancing gradually for 30 years. It is a discontinuity. A jump to a point on the energy density chart that the industry's consensus projections placed in the early 2030s at the earliest. In practical terms, an electric vehicle equipped with condensed matter battery cells at this density could drive approximately 500 miles on a single charge using a pack no heavier than current 300-mile packs. The weight stays the same. The range increases by 2/3. Or the range stays the same and the pack shrinks dramatically, reducing vehicle weight and improving efficiency in every other performance category simultaneously. But here is the detail that most people missed when this announcement landed, and it is the detail that changes the scale of what we are actually talking about. CATL did not announce this battery for cars. At the Shanghai Auto Show in April 2023, when the condensed matter battery made its public debut, the primary application CATL discussed was not electric vehicles. It was electric aircraft. Aviation operates under one constraint more absolute than any other: weight. Every kilogram added to an aircraft has a compounding cost. More weight requires more thrust. More thrust requires more fuel, or more battery capacity. More battery capacity adds more weight, which requires more thrust. The math spirals. Electric aviation has been technically feasible at small scale for years. The barrier to regional passenger electric flight, the kind that could replace short-haul routes currently served by regional jets, has not been motor technology or control systems or aerodynamics. It has been battery weight. A pack heavy enough to power a regional flight of 300 to 500 miles has been heavy enough to make the aircraft unable to carry a commercially viable number of passengers. 500 watt-hours per kilogram breaks that equation. The energy available per unit of weight crosses the threshold where regional electric passenger aviation becomes commercially viable. Not theoretically, not with further development. With this battery, at this specification, now. COMAC, China's Commercial Aircraft Corporation. The company building the C919 narrow-body aircraft to challenge Boeing and Airbus in the commercial aviation market, was already in partnership discussions with CATL at the time of the announcement. The same organization attempting to break the Western duopoly on commercial aircraft was simultaneously positioning to integrate the battery technology that makes electric regional aviation a near-term reality rather than a distant aspiration. Here is the part that should make you stop and sit with the full picture for a moment. CATL currently supplies batteries to Tesla, to BMW, to Mercedes-Benz, to Volkswagen, to Toyota, to Stellantis, to a list of manufacturers that collectively represents the majority of electric vehicles sold anywhere on Earth. Roughly 37% of all EV battery supply globally runs through CATL's factories. The companies buying those batteries have designed their vehicles around CATL's cell dimensions, their battery management systems around CATL's specifications, their manufacturing processes around CATL's supply timelines. That supplier just developed a battery technology one full generation ahead of anything its customers can produce independently. And its customers cannot easily switch suppliers, because doing so would require redesigning their vehicle platforms from the ground up. A multi-billion-dollar, multi-year process that would take them further behind, not ahead. The companies that thought they were buying a component from a vendor are discovering they have become structurally dependent on a technology leader, and that leader just moved the boundary of what is possible further than anyone's roadmap had accounted for. Step back from the battery chemistry and the aviation application, and the supply chain leverage. And look at the pattern underneath all of it. Because the condensed matter battery is not an isolated development. It is one more data point in a pattern that has been forming for long enough that it should no longer be surprising, and yet somehow keeps catching the rest of the world off guard. In 2010, China's solar panel industry was a small fraction of global production capacity. By 2025, China manufactures approximately 80% of the world's solar panels, and the cost of solar electricity has fallen by more than 90%, driven almost entirely by Chinese manufacturing scale. The technology was invented in America. The industrialization happened in China. In 2010, China's battery manufacturing capacity was negligible relative to Japan and South Korea. By 2025, China produces more than 75% of global lithium battery supply. Battery costs have fallen 97% since 2010. The technology foundation came from research distributed across multiple countries. The manufacturing dominance belongs entirely to one. The condensed matter battery follows the same pattern, with one additional element that makes this iteration more consequential than the previous two. In solar panels and standard lithium batteries, China's advantage was primarily manufacturing scale and cost. The underlying technology was broadly understood and accessible. Other countries could compete on technology even when they could not compete on cost. The condensed matter electrolyte is not a manufacturing advantage. It is a technology advantage. The specific approach, the quantum materials science, the processing methods that achieve the condensed matter state at commercially viable scales, the manufacturing processes that produce consistent results across millions of cells. These are not publicly documented. They are not available for competitors to reverse engineer from a teardown. They represent years of proprietary research that produced an approach nobody else in the industry was pursuing. Here is what most people will never hear about the solid-state battery programs that Toyota, QuantumScape, Samsung, and Panasonic have been running for the past decade. They are all working on the same fundamental approach, replacing liquid electrolyte with a ceramic or polymer solid. The physics challenges of solid-state are well understood and extensively documented in the public literature. The problems are real and they are hard. Ion conductivity in true solids is lower than in liquids. Manufacturing at scale requires processes that do not yet exist commercially, and the interface between solid electrolyte and electrode degrades in ways that affect long-term performance. None of those programs is working on condensed matter chemistry. None of them had identified the condensed state as a viable path. When CATL's results were published, the response from competing research teams was not, "We were about to do the same thing." It was, "We need to understand what they actually built before we can evaluate how to respond to it." That gap, between needing to understand what someone built before you can respond to it, is a different kind of competition than catching up on manufacturing cost. You cannot solve it by building more factories. You cannot solve it by hiring more engineers. You have to go back to the research and find a path that produces comparable results, which requires first understanding the path that was already taken, then finding an alternative that is not already protected by the patents CATL has been filing since the condensed matter program began. The timeline for that process, being generous, assuming well-funded programs move faster than historical precedent, is 5 to 8 years. By which point CATL will have had 5 to 8 years of manufacturing experience, cost reduction, and second-generation development on a technology that currently has no competitor. Now bring this back to the question that the automotive industry is quietly asking in meetings that are not being summarized in press releases. When Tesla negotiates with CATL for battery supply, Tesla is negotiating from a position of dependence. CATL supplies roughly 30% of Tesla's battery cells. Tesla has been working to develop its own cell technology, the 4680 format, specifically to reduce that dependence. But the 4680 at its best projected specifications does not approach 500 watt-hours per kilogram. Tesla's path to energy density independence leads to a destination that cattle has already passed through on the way to somewhere further. When BMW negotiates with cattle, it does so knowing that its entire electric vehicle lineup runs on cattle cells, that redesigning around a different supplier would take years and cost billions, and that the supplier it depends on just demonstrated technology capability that BMW's own research division cannot match on any near-term timeline. The companies that built the electric vehicle industry by betting on batteries as a commodity input, a component you buy from the lowest cost qualified supplier, are discovering that their supplier has become a technology leader in the most critical component of their core product. And in the automotive industry, the company that controls the most critical component does not stay a supplier indefinitely. CATL already sells vehicles in China under the Avator brand, the joint venture with Chang'an and Huawei that has been making its way into Western markets. The battery company is already a car company. The condensed matter battery gives that car company a technology advantage over every vehicle it competes with in the premium electric segment. The honest assessment of where this leads requires sitting with a question that the executives of every major Western automaker are already sitting with, and not finding comfortable answers to. When the company that supplies your most critical component develops technology a generation ahead of anything you can produce internally, when your vehicles are designed around their specifications, your supply chain runs through their factories, and your customers are already buying products that carry their cells, at what point does the label on the hood of the car stop being the relevant question? You are watching a battery company become the most important company in transportation, not by building cars, by building the thing that makes cars possible, and then making that thing so much better than anything else that the distinction between supplier and manufacturer stops being meaningful. So here is the question worth sitting with after everything in this video. If the company that makes the battery is a generation ahead of the company that makes the car, if the supplier controls the technology that determines how far the vehicle drives, how safely it charges, and whether it can eventually fly, who is actually building the future of transportation? Drop your honest answer in the comments. And if this video showed you a shift in the technology race that most headlines are still catching up to, hit like and subscribe, because the next move in this story is already being made in buildings most of the world has never heard of, and we will cover it the moment it becomes clear what they built.